Good day, everybody, and welcome to our webinar titled FCTO Consortia Overview, which features information on FCPAD and HyMARC. My name is Chris Worth, and I am the organizer for this meeting. We'll begin shortly, but first I have a few housekeeping items to tell you about. Today's webinar and slides, along with the questions and answers, will be posted to the EERE website in about 2 days. We will send out an email to attendees once those are posted to the site. All attendees will be on mute throughout the webinar, so please submit your questions via the questions box that you should see on your webinar panel. We will cover those questions during the Q&A at the end of the presentation. Please note that any questions not related to the technical aspects of the consortia, for example FOA questions, will only receive a written response when the questions and answers are posted with the webinar slides. With that, I would like to introduce our DOE host, Dimitrios Papageorgopoulos and Ned Stetson, joining us from the Department of Energy headquarters in Washington, D.C. Dimitrios and Ned are program managers in the Fuel Cell Technologies office. Good afternoon, Dimitrios and Ned.
Good afternoon or good morning for those of you on the West Coast, and by the way, Happy New Year to everyone. This is an exciting time for us, as we are launching 2 new collaborative research consortia, Fuel Cell Performance and Durability, FCPAD, and Hydrogen Materials Advanced Research Consortium, HyMARC. These 2 consortia share a common basic structure that consists of 2 primary parts, a core team of national laboratories that is charged with carrying out the foundational research and developing the tools and understanding to accelerate progress in their field, and also to work with and assist individual projects selected through competitive processes to accelerate their research objectives. The 2 core teams were selected in fiscal year 2015, and their activities were kicked off at the beginning of fiscal year 2016. We are now entering the second phase of establishing the consortia, which is selecting the first round of individual projects to work with the national lab core teams. On December 10th, the office released a funding opportunity announcement within which topics of area of interest 3 are for selecting projects for FCPAD and HyMARC. By applying to either topic of AOI 3, area of interest 3, the applicant indicates they are willing to work collaboratively with the national lab core teams. The core national laboratories for FCPAD and HyMARC are being funded through the annual operating plan process, also known as the AOP process, and therefore are not expected to apply to this FOA as either a prime or a subrecipient applicant. What this means is that applicants do not need to negotiate with the core national laboratory team members and get commitments from them. By definition, all projects selected through these topics are expected to work collaboratively with the core teams. So one thing that we've added to our site quite recently is an optional partner registry for the 2 consortium topics. So if Chris, if you can load the slide, we've got the URL posted there. And basically, FCTO has developed an optional partner registry, which is intended to pair up potential applicants to either of the consortium topics as part of our FOA. So potential partners, if they desire to do so, are invited to self-identify their interests and teaming on either of those topics. And directions are can be seen to the actual posted URL. So today we're pleased to be able to introduce Dr. Mark Allendorf of Sandia National Laboratory, who is the director of HyMARC, and also Dr. Rod Borup of Los Alamos National Laboratory, who is the director of FCPAD, and provide them the opportunity to introduce the 2 core national laboratory teams and their plans for the respective consortium. Now it is my pleasure to introduce Dr. Allendorf. So Mark, it's all yours.
Hello, everyone. It's a real pleasure to be able to tell you about HyMARC. We're very excited about this opportunity to make a real impact on hydrogen storage and hydrogen storage materials. HyMARC is a collaboration of 3 national laboratories, Sandia National Laboratories in Livermore, California, Lawrence Livermore National Lab, and Lawrence Berkeley National Laboratory, and is, of course, funded by the EERE Fuel Cell Technologies office. Next slide, please. So I'm going to cover the concept of HyMARC and its objectives and goals and organizational structure. And then I'll give a brief overview of some of the capabilities that we have. It's not an exhaustive one, but hopefully give you an idea of the things that we are both targeting and that we have already. Next slide. So the motivation for forming HyMARC is the recognition that in spite of a great deal of research and materials discovery to identify solid-state hydrogen storage materials that would meet DOE targets, we're still at a stage where there are essentially no materials that can meet all of these targets. And this graphic shows this. All those little dots are data that are taken from the hydrogen storage materials database. And you can see the square where the DOE targets are. And it's obvious that neither sorbents or metal hydrides are capable of meeting these. Now, there are some deep scientific issues that are associated with these. And last January, there was a sort of summit meeting at NREL at which a large number of PIs that have worked in the hydrogen storage area for some time met and identified some of these critical issues. So, you know, the obvious things are things like the lack of volumetric capacity at operating temperatures for sorbents. For metal hydrides, it's limited reversibility and kinetics. But there's a number of them here, and we've essentially prioritized these in HyMARC to guide our research and the development of the capabilities that we want to have. Next slide, please. So one of the things that we recognized right off is that there are a large number of phenomena that contribute to the limitations of these materials. So in this schematic, you can see various chemical and physical processes that are known to occur. So for example, in any storage material, one would assume that surface chemistry plays some role. For a hydride, for example, molecular hydrogen in the gas phase has got to adsorb and then dissociate. So there are processes that occur on the surface. But then there are other processes where that hydrogen then has to diffuse into a solid-state material. Alternatively, for things like sorbents, where these phase boundary interfaces are not really an issue, the energetics of the hydrogen and its diffusion into the material can be limiting factors. So we've taken this as a sort of high-level concept for structuring the research in HyMARC. Next slide, please. So I want to make very clear what HyMARC's objective is. Our job is to provide the fundamental understanding of these phenomena that govern both the thermodynamics and kinetics of hydrogen storage materials, and then enable the development of onboard solid-state materials. And the key word here is enable. HyMARC's job is not materials discovery. It is to go into the underlying phenomena that are limiting our ability to develop breakthrough materials, and also to develop capabilities that the wider research community can use. And we want to make these capabilities available to the community so that we can accelerate this materials discovery. This will be done collaboratively through the individual projects, as was mentioned earlier, but also through things like online databases that will be gradually built up as the HyMARC work progresses. Next slide, please. So we have a set of ambitious goals that essentially focus on providing a set of resources that can be used by projects that are supported by FOAs. So these are briefly described here. A major emphasis of HyMARC is the development of multi-physics software that can be used to model hydrogen storage materials at all relevant length scales. High-powered computing is a major capability within HyMARC, and there are contributions from all three laboratories. Coming out of this, we want to develop an extensible database framework where we can report measured and computed material properties. And in case that terminology doesn't mean anything to you, extensible in this case means that the database will be enduring from platform to platform. We're trying to eliminate problems that occur when a database, loaded onto some server experiences a change in the software or a change in funding or whatever. We want it to be available and as much as possible be immune to those things. From a synthetics point of view, we want to provide protocols that will allow people to synthesize standard materials in bulk and nanoscale formats. We want to provide ultra-high pressure synthesis and characterization facilities. An interesting note here is that in the days of the hydrogen storage centers of excellence, we basically targeted 100 bar as being the maximum pressure at which we could expose a storage material under standard conditions or practical conditions. But now that countries in the state of California, for example, are actually building fueling stations, they are using 700 bar. And so interestingly, this creates an opportunity to do both research, but actually also to develop materials that could operate with those capabilities. And finally, we're developing in situ and ex situ characterization tools that will allow us and others to probe spectroscopy, structure, and surfaces in these materials. This will involve capabilities both at the consortium partners, but will also include cutting-edge tools at the Advanced Light Source and Molecular Foundry, which are BES user facilities, and I'll tell you a little bit more about that later. Again, we want to emphasize that we want to make these consortium assets available, and that's going to be done through collaborations and the FOA mechanism. Next slide, please. So conceptually, we have broken the energetics of hydrogen storage into two pieces. At least in my research experience, there was a strong emphasis on the heat of desorption or adsorption, the enthalpy of adsorption, which certainly makes some sense. But when you think in particular about metal hydrides, it's well known that reaction kinetics are also a major contributor to their limiting behavior. So we've defined something that we call an effective thermal energy for hydrogen release that is simply the standard enthalpy of desorption plus an activation energy if it exists. And conceptually, this allows us to break up the research into basically two pieces, thermodynamics and then kinetics of uptake and release. And kinetics has a number of different components as listed here. But if we go to the next slide, you'll see where this fits in. Next slide, please. Yeah, so in this schematic, I've just added these bubbles to show where individual tasks focus on these phenomena. So off to the left, you see task 1 that focuses on the encompassing thermodynamics. But if you look at task 3, that is dealing with surface chemistry. Tasks 2 and 4 are related to processes that are primarily important for metal hydrides. These are things like grain boundary diffusion, phase transitions, and interfaces, buried interfaces. And then we have task 5, which is focused on what we're calling additives. Some people in the past have called them catalysts, but the truth is we don't really know how these materials function. So we're creating or using the term additives to be as eclectic as possible. So next slide, please. This is a schematic of the organizational structure. As was mentioned, I'm the director. I'm at Sandia National Laboratories in Livermore, California. The leads of the other two consortia labs are Brandon Wood at Lawrence Livermore. Brandon's actually on the phone here. And Jeff Urban at Lawrence Berkeley National Lab. Each of the tasks has a lead, as is shown here. And we also have individuals who are our points of contact at the two user facilities, David Prendergast at the Molecular Foundry and Jinghua Guo at the Advanced Light Source. Next slide, please. So I want to make clear that the research is not stovepiped along these three consortium partners, although nominally there are sort of individual responsibilities. So Sandia nominally leads synthetic efforts, Lawrence Livermore computational modeling efforts, and Lawrence Berkeley characterization. You can see from this chart that really this is a very horizontally integrated project where all three consortium partners contribute essentially to all of the tasks that are occurring. So for example, you'll see that in task 1, Sandia is leading this effort to make materials for understanding the thermodynamics, but we're also providing them for all the other tasks. Similarly, Lawrence Livermore has deep expertise on porous carbon materials, and they are providing those to the other tasks, and Lawrence Berkeley is working on some new nanoscale technology. Task 6 does not have any activities this fiscal year. It is focused on database development and will be launched next year. Next slide, please. Yeah. So in the time available, I will quickly go over some of the capabilities that HyMARC has. I want to emphasize that some of these are available right now. Some are things that we are going to develop. So I'll try to make that clear, but I think that as part of the proposal writing process, you may want to consult with DOE people or ask questions about specific capabilities if you're unsure if they're available immediately, and we can try to provide information along those lines. This is a list here, and I'm just going to skip through various ones of these quickly right now. So next slide, please. So multi-scale modeling, as I mentioned, is a key component of HyMARC. We have tools that are meant to simulate phenomena that go all the way from the atomic or molecular scale up to phase fields, i.e. phase transitions, nucleation, diffusion along grain boundaries. Our intention is that we will use these in concert to develop a comprehensive picture of how these materials are behaving. Of course, this is a very large scientific problem and is not going to be solved tomorrow. But these tools are in place, at least the basic components are, and they're going to be developed and adapted for understanding hydrogen storage materials. Next slide. An example of these is quantum Monte Carlo, which has not really been used to model energetics and hydrogen storage materials. And an example where we would be using this is to try to quantify accurately the interaction energy of molecular hydrogen with an open metal site on a metal organic framework, or a dopant in a porous carbon. These are interactions that are relatively weak but stronger than physisorption, and as a result, they're difficult to model. So Brandon Wood's team at Lawrence Livermore will be employing this tool to develop a more detailed understanding of these energetics. Next slide. Another example is the solid-state phase transformation kinetics modeled by phase field modeling. Again, this is a tool developed at Lawrence Livermore. The basic idea here is to be able to look at relatively large scale, as large length scale processes such as nucleation, where there may indeed be not just processes at a buried interface that we'd be concerned about, but also processes that are affected by polycrystallinity or morphology of the material. There's some references that are listed here if you'd like to find out more about this. Next slide. Now, our plan is to have a suite of sort of model sorbent materials that we will be characterizing to provide data for computational modeling. So, for example, we will have a library of MOFs that contain specific structural motifs that can be used to develop accurate force fields. For example, that materials with open metal sites. We plan to eventually adapt this to account for effects like morphology, additives, nanoparticles in their different surface areas relative to bulk materials. So this is an effort which we've launched right now with the start of the project and will be ongoing throughout the life of HyMARC. Next slide. We have extensive synthetic capabilities here that are in place. So for both bulk and nanoscale metal hydrides, Sandia in particular has extensive equipment for ball milling under hydrogen at various pressures, very high pressure reactors, and other characterization capabilities. We expect to be bringing online sometime this summer an ultra-high hydrogen pressure reactor that can go up to 700 bar, accessing these realistic fueling conditions as I mentioned earlier. Next slide. Lawrence Berkeley Lab, Jeff Urban's group, is developing graphene nanoribbons as a way of looking at nanoscale phenomena and being able to understand both the very local structure and being able to incorporate catalytic or additive centers in locations where they can be very precisely characterized and controlled. So these are new materials that they've developed. They've shown that they can be effective with magnesium hydride, and we're going to be extending this to other hydrides, working our way from simpler to more complex hydrides. Next slide. They are also expanding these to add additives, as I mentioned, and listing some of the various hydrides that they eventually plan to incorporate. Let's move quickly to the next slide. Sandia has essentially unique instrument called low energy ion scattering that is optimized for looking at hydrogen interactions with surfaces. It is perhaps the only way to actually detect hydrogen directly on surfaces, highly sensitive to the surface. It can distinguish between hydrogen and deuterium, and we'll be implementing a capability to allow us to look at adsorption kinetics and diffusion on surfaces within the first year probably of the project. This is a capability that will be available to projects that are proposing to the FOA. Next slide, please. I've got 1 minute left, so I have to go fast. The user facilities, such as the Advanced Light Source, are going to bring capabilities that are really at the cutting edge and were not available when the original centers of excellence were operating back in 2005, 2010. One of them that we'll be using is ambient pressure X-ray photoelectron spectroscopy. Now, this is a user facility, and these materials are very much in demand. So these are going to be research tools for the HyMARC team. Initially, we are going to be building up specific tools that are needed to make them useful for hydrides. So these are not going to be immediately open to use by the broader community, but we hope that we'll get to that point after the initial phase of HyMARC. Next slide. I think I'm actually out of my time, so maybe we skip through. Let's go to the next one. I want to just mention that we also have a theoretical component at the Molecular Foundry that uses computational spectroscopy to interpret these soft X-ray data. Next slide. And finally, we're going to be developing community tools, as I mentioned, which are databases that will be available to anyone, not just people responding to FOAs. And this will also include eventually open source software that can be used by researchers focusing on specific storage materials. So that finishes my presentation. I just want to thank the Fuel Cell Technology Office again for supporting this work. And after the next presentation, I'll be happy to answer any technical questions there are. Thank you.
Thank you, Mark. So next up we have Dr. Rod Borup from Los Alamos National Labs who can talk about FCPAD. So Rod, go ahead.
All right, thank you. I'm pleased to present the FCPAD, which is, as I've said, the Consortium for Fuel Cell Performance and Durability. So the acronym is pretty directly understandable. And like HyMARC, this is funded out of the Fuel Cell Technologies Office from DOE. So in terms of FCPAD, the core team is made up of 5 national labs, as it was proposed for the core consortium, and this started again in the beginning of FY16, so it's still in the developmental stages, but it's only about 3 months old. And this includes labs and staff which were, highly involved in prior competitively awarded related projects on durability, transport, MEAs, and similar type things that fit into this topical area. So FCPAD is available to provide technical expertise and harmonize activities with other developers, including industrial OEMs, component suppliers, and academic institutions. So I think you see that HyMARC and FCPAD, while the topical areas are very different, the objectives and how we want to interact with other organizations are probably very similar. FCPAD, in terms of bringing together those previous smaller individual projects, it's just not an extension of those projects, but it integrates them into a better performing, larger project that then amplifies FCTO's impact beyond those smaller level projects and provides these capabilities, to new projects coming in. And I think you can see the 5 labs logos on the first slide, and you'll see I'll talk about more of those labs in a little bit. You can go on to the next slide. So the approach on how we're developing FCPAD includes, and this is a little bit straight out of 1412 FOA, we expect to see additions into the core national lab team that makes those capabilities available to different academic institutions, industrial developers, and other national labs that can add capabilities into FCPAD. I want to be clear, and I'll probably mention this later, we're interested in working with other institutions from the FOA. We are also interested in collaborations with institutions that aren't interested in the FOA or for some reason are not available in that. We want this consortium really to speed the development of these fuel cell components. So with the consortium team, there's experience related to the performance and durability. The way we've designed this, it's made for an influx of new innovative ideas to the core team, although we've got a lot of experience in the core team related to performance and durabilities, making these capabilities available to foster these new ideas and collaborations. You can move next slide. So our overall objectives, again, similar to HyMARC, different topical area, but the main objective is to advance the performance and durability of polymer electrolyte membrane fuel cells at a pre-competitive level to further enable their commercialization. Most of the work that we envision in FCPAD, especially from the National Lab Consortium, will be at a pre-competitive level. Our job is to do the foundational science, develop the knowledge base, optimize structures for more durable, high-performing PEMFC components, and at the same time keeping in mind that we still have to reduce cost, and so that's an emphasis. So FCPAD is aimed at the FCT roadmap and targets. Thus, the primary target is high performance at low platinum loadings, trying to meet the DOE targets, which are normally about a total platinum loading of 0.125 milligrams a square centimeter, yet obtaining high voltages at relatively high current density, say 1.5 amps a square centimeter. So FCPAD is looking at the higher performance, the durability, reducing component cost. However, FCPAD is not really designed as a synthesis consortium. For example, our role really is not to synthesize new catalysts. However, implementing new catalysts, new structures to obtain the higher performance and durability is among our objectives, and so we're very interested in working with people that develop new materials, for example, out of different FOAs, for example, the catalyst FOA that was announced recently. Next slide. This is only one of the target tables from the DOE roadmap. This is related to MEAs, and we do concentrate significantly on the MEA component in FCPAD, but I recommend that people look at the other target tables, in terms of what the status is and where we need to go in terms of cost and durability. And as we improve durability, we can't do that by sacrificing cost, and obviously there's a big interaction between cost and durability. Obviously, as you put in more catalyst in a fuel cell, you can improve the performance, but you're sacrificing cost. Recognizing that the DOE roadmap is primarily related to transportation activities, thus we have to keep in mind the different target metrics include shutdown, startup, power cycling, and operating conditions conducive to transportation, including inlet relative humidities, temperature, pressure, are amongst the key performance and durability operating constraints that have to be kept in mind in terms of FCPAD. Next slide. So we've broken the core lab consortium structure into different thrust areas, and specifically, and I've got a slide right after this, which is more graphical in nature, but there's 3 component thrust areas, and there's 3 cross-cutting thrust areas with different coordinators for the different thrust areas, and I want to make sure people understand that these consortium capabilities related to these thrust areas are available to support collaborations that will be awarded in the FOA 1412. And we do desire collaborations outside the FOA process for institutions that for some reason don't want to participate in that or for some reason are not eligible. So if you go on to the next slide. Graphically, I think you can see vertically the 3 component thrust areas are divided into electrocatalysts and supports is one. The electrode layer and the structure is thrust area 2. Other different components, including ionomers, membranes, GDL, bipolar plates, is thrust area 3. And hopefully you can understand the cross-cutting areas such as modeling and validation, cross-cut 1, 2, and 3, operando evaluation, and I've got a slide for each of these thrust areas later on in the presentation. Component characterization is obviously relevant for all 3 of these, and we're looking at how we include other labs, industry, and academic into the core team, and how this core team conducts the foundational science to support these new and developing different component and capability areas. So next slide. So I think this details a little bit about how our structure is. I didn't put pictures of each of the thrust area coordinators, but the director for the center or for the consortium is myself from Los Alamos. Deputy director is Adam Weber out of Berkeley. And then we have different coordinators for the 6 different thrust areas that represent all of the 5 core labs in them. And I think you can read their names. Debbie Myers is coordinating electrocatalysts and catalyst supports. And I should mention that all these coordinators are senior level national lab scientists that have been involved in these thrust area roles, which is why they were chosen for those roles. And Debbie's looked at a lot of electrocatalyst and support durability over the last decade or so. Sham Kocha from NREL is the coordinator for the electrode layers, and he's been working in a similar role, developing new electrode structures out of some of the different materials out of NREL, such as the extended thin film structures. Adam Weber has a core role, including the deputy director, but also coordinating ionomers, membranes, and GDO, bipolar plate, and interfaces. Rajesh Aliwalia, we've been interacting with from Argonne. He's been doing a lot of the modeling, and so he's the coordinator for the modeling and validation area. To say that one person from a lab is the coordinator doesn't necessarily mean that lab is doing all of the work. The coordinator roles are somewhat complicated, including they have to coordinate for the different labs that are in those thrust areas and then outside of the thrust areas as we add other organizations into the FCPAD. Mukundan from Los Alamos is coordinating Thrust Area 5, which is operando evaluation, which includes benchmarking ASTs, contaminants, and Karen Moore from Oak Ridge. Most people I think are familiar with, for running the microscopy lab there, is the coordinator for a lot of the characterization and diagnostics that'll be both utilized inside of FCPAD and newly techniques developed inside of FCPAD. Next slide, please. So this is just an example of how we've coordinated in the past, and there'll be an emphasis on how we coordinated in the future to amplify FCTO's impact beyond smaller individual project levels. This is discussing, how, for example, in the past, Trust Areas 1, 2, and 3 have done different evaluation, performance, and durability related to components. And then how we've interacted with the thrust areas in terms of characterization and modeling, and we'll be working highly to coordinate from the different modeling areas or the different cross-component areas with the component areas. And this is just one example of in the past where we've done a lot of carbon corrosion work with Argonne, Los Alamos, and Oak Ridge doing modeling, characterization, and a lot of the experimental area. So next slide, please. For FOA 1412, again, we're interested in participating with people who are interested in that FOA. How this coordination works will be determined by DOE, what the subject area is, and obviously the participant interest. And I want to make it clear that we're interested in organizations that participate in FOA 1412 and also outside interests. We're trying to speed how the collaboration goes, so we've done things like there is a multi-lab NDA that is nominally completely written. We're working through the approval process now, so hopefully organizations that want to share data on and keep some of the proprietary information close to the vest, there's be one NDA for all the different labs involved in the process. Hopefully that will speed a lot of these agreements so that they don't have to go out and do these individually. We're going to continue holding annual working group meetings related to durability and transport. We'll be participating in the annual merit review, fuel cell tech team reviews, along with all of our individual staff scientists participating in all the National Society meetings that we've done. I wanted to stress some of the data sharing that we intend to do. We do have an internal website that's open now that we're starting to put data on. We also are developing an open website that data will be going on that will be searchable and available to the developers out there that are interested in that. Hopefully that'll be available in the not so far distant future. And for those that don't want necessarily all their data shared, there'll be a hierarchical authorization type process, that they can keep their intellectual proprietary data, to those that they only want to see it available to. Next slide, please. So this is a slide just, again, on the structure of FCPAD, and then I'll get into the thrust areas. We have the 5 national lab core teams. We're working with all 5 lab technology transfer areas, so that we can have some easily good, quick, fast agreements that can be done with people. We're developing both internal and external websites to help share data, both inside of FCPAD and with outside of FCPAD. And from the core labs, we've got available our technical experts that are available to help people with their technical expertise, and that forms a steering committee we'll add into that steering committee associate members that are awarded projects out of the FOA, and we continue to take advice and input from people who are willing to come to the Durability and Transport Working Group meetings and USS Drive. And of course, this is funded out of FCTO, and so FCTO is responsible from their program management, the overall management of what the FCPAD consortium does. Next slide. I've got 2 slides related to capabilities. I won't go into these in detail. They're going to be available, but we tried to cover a lot of the capabilities that are available in the national labs for organizations interested in FCPAD. This isn't a complete list. And if we go to the next slide, while the previous slide was more graphical and pictures, this is a list. Again, it's not a complete list of the techniques and capabilities available in FCPAD, but recognizing that the member labs have been involved in both performance and durability for a reasonably long time, we have a well set of capability amongst those labs that are available for developers interested in collaborations in FCPAD. So I won't go through the list, and let me talk now about the different thrust areas. So if you can go to the next slide. I've got just 1 slide per thrust area so you can get an overview of each of these, and again, online are more details about these things. But thrust area 1, the coordinator is Debbie Myers from Argonne, is related to electrocatalysts and supports, and I think you can go through and read it, but it's related to the catalyst and catalyst durability, understanding degradation mechanisms. Down at the bottom is looking at, some of the pictorial diagram of say, random alloy, platinum skin, or core shell, faceted. And then the diagram on the right is, I believe it's Zane's, of looking at the nickel platinum structures as a function of voltage. And I think that was done at APS. And again, we can make a lot of these capabilities and measurements available out of FCPAD. Again, part of this thrust area is looking at catalysts and support interactions, understanding what the degradation mechanisms is, so what they are, so that we can make more durable catalysts, and then include these catalysts into the electrode layers and get the most out of the performance. And that leads into the next slide, which is about thrust area 2 and electrode layers. And this is discussing, looking at how we make high-performing membrane electrode assemblies and electrode layers with low platinum loadings and high performance. And on the right-hand side is some of the diagnostics that are available related to electrode layers inside of FCPAD. Part of our FCPAD thrust area 2 is to understand what's going on in these electrode layers, what the structure is, what the limitations are in terms of transport and kinetics. And a different portion of this thrust area is designing higher performing electrode layers, putting in new and novel materials. And in the lower right-hand corner, I don't know if you can really see it very well, but that's an example of some work that was done related to FCPAD, where we're looking at ionomer coatings on multi-walled carbon nanotubes. So you can go to the next slide area, and we can go over the third component area, which includes membranes and ionomer films, gas diffusion layer, bipolar plates, and interfaces. And an example of some of the work that's ongoing in this area related to FCPAD is looking at some measurements done at ALS, looking at thin ionomer films on different surfaces and what those structures look like, so we can better understand how ionomers in electrode layers and membranes interact with catalysts and support materials. In the lower right-hand corner is some GDL capillary microcapillary pressure measurements, so that we can understand how liquid water goes through GDLs and microporous layer type structures, so that you can then design interfaces between the membrane, the catalyst layer, the GDLs, the bipolar plates, to get the highest performing individual cell components. So if we go on to slide 4, or the next slide, and thrust area 4, This is modeling and validation, and we've got a number of different modeling components, and the modeling component is clearly key to understanding much of what's going on with a lot of the experimental data. Shown here is some modeling of the electrode microstructure, simulating and modeling how and what the different concentrations of oxygen is in the microstructure related to the ionomer. There's several different modeling approaches being implemented in FCPAD, and a key to the thrust area coordination is co-design of experiments with the modeling, which I showed previously, and then the modeling component, helps with the experimental data analysis and understanding what's going on in the component thrust areas. So if we can move on to thrust area 5. This is looking at operando evaluation, benchmarking, accelerated stress tests, different contaminants, and some examples here are doing segmented cell studies at the FCPAD consortium between the member labs. We have the ability to run all the ASTs that have been recommended that are out there, different drive cycle testing, different methods of shutdown startup, some freeze work looking at durability testing of the different components, including catalyst membrane, GDLs, bipolar placed MEAs, and part of this thrust area will be looking at trying to understand what the state of the art is and in terms of durability and benchmarking the durability of different materials. And one of the other parts of that is looking at contaminants and impurities in terms of the durability, primarily from the different system contaminants and air contaminants. So if you can go to the next slide, that's thrust area 6, is looking at characterization, and this again is a cross-cutting thrust area that will be used for all the different thrust areas. And this is one of the ways that the national labs can be greatly beneficial, especially to some small businesses that don't necessarily have all the characterization capabilities that are available at the labs, including several of the different beamlines, so for example, APS and ALS. On the left-hand side is shown some of the microscopy facility that's available at Oak Ridge, and they've been interacting with a lot of different developers over the years. In the lower left-hand corner, I think, is some Zane's work looking at the different structure of different catalysts. And while we don't necessarily own the different beam lines, we've got scientists involved in FCPAD that can help make these beam lines, I think, more useful and help facilitate using some of these characterization tools, for other different developers' projects out there. And then I think if you go to the next slide, I think this is my last slide. And again, I wanted to thank FCTO for funding FCPAD and making it available to interact with different developers, and then say that from the 1412 FOA, there's a link to some of the things, and if you click on the link that's on that slide and then click a couple more times, you end up with a second link, and there's a more detailed set of slides that are available out there related to capabilities and the organization activities inside FCPAD. And then the third link I put down at the bottom is the FCTO multi-year RD&D plan that's got all the target tables and where we see the program going to speed fuel cells, enabling the different components for commercialization. And I think I'll stop there, and hopefully we've got time for questions. And I didn't say it, but I think all the different coordinators for FCPAD are on the line the last time I looked, available to answer questions.
All right, thank you, Rod. So we do have time for a few questions. We do have a number of questions submitted. As you can see on the screen now, how to submit questions is shown. So if you have questions, please submit them. As Chris mentioned at the beginning of the webinar, we will take all questions which are related to submitting to the FOA and procedural parts of the FOA and answer those only through posted responses, and they should be posted in the next day or two. Today, we will respond to questions which are technical in nature. We do have several questions. Let me start with one which is not quite technical, but this DOE HyMARC will help us identify a new cost share partner. We'll respond to this one because, as Demetrius mentioned at the intro, we did just establish a new partnering website. The only involvement DOE will have with helping to identify partners is through that site. It is basically a passive site where you're able to download a PDF, complete the information in PDF, submit it back, it will be posted, and that'll be a site to help partners identify additional partners, or applicants identify additional partners. That is the only involvement DOE will have with helping to identify partners. Another question is, will this presentation be made available online after the call? As we said at the beginning of the webinar, presentations as well as responses to the questions submitted will be posted within about 2 days after the webinar. Okay, new electric catalysts and supports will also be covered with this DOE for Demetrius.
And the short answer is no. The development of electric catalyst supports or membranes is not a part of FCPAD. They're not a part of the FOA, and that has been stated in the FOA itself.
Okay, we do have one here for the two. I believe they've actually already, or at least I think Raj has answered it. Will you be sharing the contact information for the coordinators for the various special areas? So Rod, you said yes, it's posted in your presentation.
All of the coordinators are listed. I'm not sure if I've got email address, but obviously we can put that on the website. I think all the coordinators are easily searchable, and if you look at, for example, the FCTO previous AMRs, we've all given presentations there, so we should be pretty easy to find, but we can post that along with the slides.
And Mark, for the HyMARC press coordinators?
Sure. My slide just gives the names, but I can augment that with a list.
Okay. Another one, which again will give the both directors. Please give an indication of industry interest in participating with HyMARC and FCPAD. So, Mark, have you received industry interest?
Yeah. Are you asking me?
Yes.
Yeah. There's been some interest. Generally, I've been referring specific inquiries and questions to the EERE exchange and this webinar, but there has been some interest.
Okay, and Rod, for FCPAD?
Again, we've gotten significant interest. I've had a lot of contacts, and like Mark, I've been, since the FOA issued, been referring them to this webinar and the slides that are online. You know, we did talk to some people before the FOA came out to make sure that they knew that FCPAD was being developed. You know, from our side, you know, clearly we are interested in industry and academic participation. I think there'll be a significant interest out there, but obviously, you know, that depends on, you know, what industry types are out there.
So Rod, another question for you that came in, and that is whether FCPAD is concerned with the development of new materials or whether it just takes in new materials.
So the example that I gave was related to catalysts. FCPAD is not looking at synthesizing new catalysts. DOE FCTO has a specific catalyst program, and so that's clearly outside of the scope of FCPAD. We are very interested in getting those new materials and helping, for example, the awardees in that catalyst proposal and helping them make MEAs and higher performing MEAs at low current densities. In general, FCPAD is going to do the foundational science to understand how to make materials form, what the durability is like, and not be a synthesis. I think we do have some interest in taking existing materials and trying to make them better in terms of, for example, performance and durability. But new synthesis materials, I do believe, will be handled by other FOA type processes.
So another one, Ron, for you.
as it comes in? Is it also an objective for FCPAD to review and develop new AST protocols?
So new AST protocols is part of our thrust area 5. We are trying to refine them. There is a significant effort that's been ongoing, and we've had some meetings with outside the U.S. organizations to try to harmonize AST protocols worldwide, and that effort will continue to try to come up with the best protocol, AST protocols and other types of protocols, so that you get uniformity both within the United States and internationally. And we are trying to develop other ASTs. One example is an AST for GDL materials, which there doesn't really seem to be one that has been accepted by, for example, the fuel cell tech team. So that is a part of our thrust area 5.
All right, thank you, Rod. Mark, for HyMARC, there's a question. Do you have in-situ monitoring capability to go with high pressure?
In-situ monitoring capability? We have some. We have, of course, PCT equipment. We are considering what we're going to add to a reactor is high pressure is 700 bar, so I can't give too much details on that yet.
Okay, one for Rod as well that came in. FCPAD for FCPAD. Is there any existing developed or expertise and understanding on GDL/MPL interface linked to degradation?
So there is both Los Alamos and Berkeley as examples, and I don't want to ignore our other team consortiums, but for example, Berkeley has been doing a lot of microcapillary pressure measurements. They've been doing 3D tomography on GDLs, trying to understand the structure. There's been both modeling, I think, from Argonne and Berkeley trying to understand the transport and thermal gradients that are induced by GDLs and how those performs at Los Alamos. We actually haven't been doing it for the last couple of years, but we did, look at GDL and MPL material degradation, if you want to rephrase it to that. But overall, I would say we're looking at how the material properties change as a function of time. That hasn't been an emphasis as of late. We do have a lot of past work that's been done on that, and we were intending to do some in FCPAD. Part of what will happen in FCPAD is as industrial interest comes in and dictates what they think the priorities are, we will shift emphasis to different materials. And I would say at the moment, we do have a significant database on GDL and MPLs, but it's been a lower priority, for example, compared to developing new characterization techniques, understanding electrode layer structures.
All right, thank you. We have another question which was directed to Rod, but I think both directors can actually respond to this one. So, will the FCPAD NDA cover interactions between external partners, for example, university to industry? Rod, do you want to start?
Well, I'll start with the multi-lab NDA, since I talked about it, was actually modified. We actually took the HyMARC one that was ahead of us and modeled ours off of the HyMARC one. As the way I understand the FCPAD one, it is an NDA that will cover all 5 national labs. I think if you want an NDA between Company A and Company B, that's probably going to have to be handled separately outside of that multi-lab NDA process. And I believe, Mark can answer after me, HyMARC, I think, is ahead of FCPAD in an IP type of agreement.
Well, yeah, essentially that's all correct. I mean, NDA or IP arrangements between team members outside of the core HyMARC, those can be negotiated independently. As far as IP that might be generated as part of a project involving collaboration with HyMARC, we encourage the simplest thing to do is simply the NDA. But if partner wants more protection than that, then we encourage using the model CRADA that DOE has developed. That is the fastest way to do it. But if there are additional concerns, then of course a custom one can be done. As I'm sure many of you are aware, that takes longer because more lawyers get involved. But at least that's my understanding of where this stands right now. We haven't finalized the one for HyMARC yet either.
All right. Thank you, both of you. We still have a lot of additional questions that have been submitted. So we'll take one last question here, and this is again for Rod. Does FCPAD have the capability to make MEAs for testing?
Yes.
So since you provided that brief of an answer, then I'll ask you another one. Are you interested in low relative humidity MEA performance?
Again, I think in that case, we are interested in supporting where developers are going for their performance. And I think when you look at the target tables, people would like to go to lower and lower RH performance. And so, yes, we are interested in low RH performance. It greatly simplifies the overall, should I say, fuel cell system. And so we're interested in doing what we believe is going to help the overall system. In those types of operating conditions, I think FCPAD really relies on a lot of the developer input in where they've seen the system specifications going. So if people are looking at, maybe for a stationary system, a much higher input RH, we're interested in helping them in those areas for transportation. The inlet RHs are being driven lower and lower, and I'm sure they'd love to see, normally a zero inlet RH. So as things are available there, we want to pursue that.
All right, thank you, Rod. So the time is now up. I'd like to thank all the presenters for their time and effort and presenting, and all the participants and all of you for listening. And with that, I'll turn you back to Chris for the wrap-up.
Thank you, Ned, and again, thank you to our speakers on a job well done, and thank you to our attendees for contributing your questions. If you have any more questions, please feel free to email the presenters directly, and they will try to respond in a timely manner, and we'll probably post those any additional questions online as well at the EERE website. I just want to remind you again that the webinar slides and questions and answers will be available online at the webinar recordings and slides link there, and you'll also receive an email from me directing you to the website once we have those posted. So thanks again, everyone, and have a great rest of your week. Bye-bye.